ever heard of the term LiDAR? Well, it's been around for quite a while. It's become very popular recently due to the rapid advancement of technology. While this LiDAR technology has been around on particularly planes and helicopters for a long time because of technology and the ability to make this equipment smaller and lighter and cheaper, it has particularly recently become quite a popular and more increasingly used bit of technology. So to help understand what LiDAR actually is and how it works, stick around and I'll help you run through this. LiDAR, it stands for Light, Direction and Ranging. And basically what that terminology is saying, you've got a sensor, it sends out a light signal at a specific angle, and which is the light part, and it's at a specific angle, which is the direction, and it then measures the time it takes for that light beam to go from the sensor to the object and back, and from that can determine a distance or a range. So LiDAR, that terminology basically results with a beam of light that you're able to determine a distance from the sensor to an object. LiDAR itself comprises of essentially three components, which include the LiDAR unit or the light sensor, and it also contains an IMU, which is an inertial measurement unit, and it also contains a GPS or GNSS receiver. So these three components basically integrate and work together to produce this, what we call a LiDAR unit. So how do all those three components work together? Basically what you've got is your LiDAR sensor. On top of it, you have a GNSS or GPS receiver. So it receives signals from satellites and can determine a position. So once we know the position of this sensor, we then can measure, using the laser, we can measure a distance from this known position to the surface, which we can then calculate the surface position. But obviously the LiDAR unit is moving. So this movement is adding another complexity to the understanding where this surface is. So the GPS or GNSS unit, as it moves along, the GNSS receiver pings its position every second or so. So there is a gap between this laser that's constantly measuring and these GPS units. So that's where an IMU comes in. It basically then determines the position between the GPS signals that it receives to then calculate a more refined, and the two of them work together to help compensate for any drift or errors associated between the two units, to then determine basically a constant position of where this laser or LiDAR unit is. So all three of these components work together to be able to constantly know where this sensor is, to then measure the ground. And then from that, this light is measuring surface or the surface below it, and from that can create a point cloud, which is commonly used in other sources of measurement units as well, but the LiDAR basically produces a point cloud and then can be used in further software for analysis. Another thing that can be attached onto LiDAR units and is particularly common is a RGB camera. Just a typical camera which is mounted on the sensor as well. It's very common these days to have an RGB camera as well, because when the point cloud is generated and viewed, you can view in a photorealistic or a color representation of this point cloud. So it basically brings what you're looking at on site, brings it to life on the computer. So there are a few different outputs you can have with LiDAR or a point cloud in general. That can be intensity. So our intensity is, you don't need an RGB camera for this. It's just the LiDAR unit itself, and it produces a point cloud, and it's viewable by when a light beam shoots to an object and returns, the intensity value is basically the return strength of that light beam from that surface. So light reflects differently off different surfaces depending on their color and their material, and the intensity of that reflection is then recorded back in the sensor. So if you have changing surfaces, changing colors or densities of surfaces, you can then get a return signal of intensity and different values, and then can be viewed on a computer screen, and often that is reflected in like a rainbow colored spectrum, and you can view your point cloud in that intensity format. You can also view it in RGB as explained before, so it's that red, green, blue color spectrum, which is what we see with our eyes. So you can view the point cloud as if what we can see. So on your screen you'll see like the green on the trees and the grass, the dirt and everything. You'll be able to interpret that. So the point cloud then, it basically drapes on these RGB colors to the points. There are other different types of formats you can produce with a point cloud as well, depending on what your purpose is, but another example might be height spectrum. So you could have, based on your elevation change of these points, you can have changes in colors at certain values. So that's another example, and there are more depending on what type of output you want, or if you want to visualize the point cloud differently, but they are three common ones that we often use. So LiDAR varies differently to photogrammetry because essentially the way that they measure is different. So LiDAR is a direct form of measurement, as it is sending out a laser signal and measuring an object and directly receiving that distance difference between the sensor and the object. Whereas photogrammetry is a little bit different because it's known as an indirect form of measurement, where it is calculating the positions of the surface by using overlapping photos and then using the parallax and pixel matching and all that algorithms behind the software processing can then determine the point cloud from that. So two different forms of measurement, but they do essentially provide the same result, which is often a point cloud, or other different formats as well included. So two differences with two different methodologies, and both have their advantages and disadvantages. LiDAR itself is often a little bit more expensive because there are different systems that comprise of the whole LiDAR unit itself. These systems work together, they're a bit more complex and are more expensive. It's not as commonly used as just, for example, a drone with a camera on it, whereas the LiDAR unit could have a camera and it'll have the IMU and the GPS and the LiDAR or the laser sensor as well. So there are more complex things on it that work together. Another thing with LiDAR is it's heavier because there's more systems on it. So often that will mean you'll need a heavier aircraft or heavier component to be able to carry this LiDAR unit. So often they are on aircraft or on drones, and to be able to carry this payload you often need a heavier aircraft to do so. However, the difference with LiDAR to photogrammetry is the LiDAR unit is a laser, so it can penetrate through things like vegetation. So if it's long grass or grass in general and trees, often the laser will go through or measure between the gaps in all the trees or the grass to get a more accurate result of the ground. Other things with LiDAR too, there are multiple returns with a laser. So when the laser beam comes out of the sensor, it might be able to hit the top of a tree and go through and hit a branch and go through and hit the ground. So you'll get multiple returns with that one laser beam. That's just a general tip when you're looking at different sensors and how many returns they have. It's probably not necessarily it's not going to help understanding on how accurate you're going to get the sensor, rather than the more important factor is the beam width. So when a laser is shot out of the sensor, the cheaper units in particular can have quite a large diameter of laser beam, and this is not good for penetrating through vegetation. So ideally what you want is a smaller laser and with multiple returns, so you can go through the vegetation a lot better. If it's a larger laser, then it's going to struggle to get through those vegetations or the trees or the grass or anything like that. So yeah, the beam width is important because often you'll pay more for the smaller diameter ones, but you do get better results and better accuracy. So don't focus so much on the number of returns per beam, because some sensors can claim that they do get a lot of returns or more returns than some other units, but the beam width is so large that it doesn't actually penetrate through the vegetation any better. Often a difference between LiDAR and photogrammetry is, as we mentioned, it gets better results with vegetation. So if you're doing surveys over paddocks or with treed areas or anything with some kind of vegetation, the best methodology is to use a LiDAR, just because it will measure through to it'll be the closest to best representing what the true ground model is. Whereas photogrammetry, using those pixels, it can't penetrate through the vegetation or the trees or the grass as well as what LiDAR does. Another benefit with LiDAR is, what we've found, is you get more redundancy. So if there is something that does go wrong with the LiDAR itself, often you can fall back to using a photogrammetry method. So there is that element of redundancy with your flights. Sometimes that doesn't work perfectly, but it does help with the reassurance, particularly on jobs where you may have to travel a long way, that if something doesn't quite go right with the LiDAR unit, you do have that backup of redundancy. Another fantastic thing with LiDAR too is often you're able to visualize the point cloud or the results of your LiDAR unit while it is flying. So the software is getting good enough where you can actually view your results while it's doing its job simultaneously. So it gives you that confidence that you can pack up and you've actually seen what your results are, so there's less chance that you'll have to come back again. Another fantastic thing with LiDAR is the ability to measure small objects. This is really important for surveyors, particularly with power lines, poles and signs, and fences. These are just some of the features that we're able to measure with LiDAR that photogrammetry can't really get, and it makes a massive difference with our surveys. Particularly what we've found useful is the power lines. So we're able to survey an area and collect so much data, including these power lines, and put it all into a survey plan to send to the client. Whereas previously, if we've used photogrammetry, we can find the ground model, and then we may have to go back on the site to determine where the power lines are, and even that can be fairly limited data, including you won't get the full information of the cables on the power lines. One important tip to note with LiDAR is, depending on the sensor unit yourself, your flying heights may change on being able to actually pick up these smaller features. So what we found is, particularly with the entry-level LiDAR units, that your flying height cannot exceed more than 50 meters between the sensor and the power lines, as an example. So if you're flying higher than 50 meters, you may not even pick up any of the power lines. They're just too small, and the LiDAR sensor doesn't recognize it. It just goes straight to the ground. So we had a job in Wagga, and this is a perfect site that we realized that we did have this limitation with this LiDAR unit, is because we set up on a hill, and this hill, it wasn't a big hill or anything, it was just slightly sloping down. We set up roughly in the middle, and we were doing our LiDAR flight, so cross-gridding over this paddock, and part of it had power lines that were running down this hill, and we found at the top of the hill we were getting clear, beautiful looking point cloud measurements of this power line. We could see the sag in it and the poles and everything. And as we got further over, because our flying height stayed the same, the distance to the power lines was increasing as we went down the hill. We found that the data was reducing to the point where we weren't getting any results with the power lines. So it then made us realize for that job and that LiDAR unit that the separation between our sensor and the object, being the power lines, is best kept at 50 meters or less. Otherwise you start getting to reduced quality or little to no results with your point cloud. Another important tip in the field is your side lap or your overlap when you're doing your LiDAR flights. So when you set up the mission, similar to photogrammetry, you'll have your grid where it just goes back and forward, and you've got an amount of overlap that your LiDAR unit measures between each run. So typically, I think some people recommend 30%. You can get that strong overlap and a good result. We like to ramp it up a little bit just because towards the edges of your LiDAR data, you're getting a greater angle between the object and your sensor. So as the angle increases, the accuracy decreases. So what we like to do is exclude or remove any data on those extreme angles, and what we do is reduce 2.5 degrees of the most outer edge to that 2.5 degrees of point cloud data. We actually eliminate that because you're getting increased or decreased accuracies. So what we like to do is delete that, but increase our flying overlap. So then we still have that a strong overlap amount, and we still get a lot of data out of it. And what we also like to do is have that redundancy, as I mentioned before. So if there is an issue with the LiDAR data, we can actually revert back to photogrammetry. So what we like to do is keep the overlap or the side lap at 55% to 70%, somewhere in that range. And ideally we try and balance it with how big your site is and how many batteries you'll need to do the flight. And it's kind of balancing. Maybe if you, rather than doing 70%, because it's going to be a large day of flying, maybe even more than one day, we might reduce a little bit just to fit it all in one day. It's kind of a little bit of manipulation there, just depending on your flying times and your site. But generally, if we can, keep it up near that 70% range, but we do have a little bit of play with that as well. Another important factor in the field is your IMU, the inertial measurement unit. This is critical to make sure that it is calibrated. So often what you will see with LiDAR units is calibrations. So these IMU calibrations help reset the IMU to be accurate, and so often you'll hear the term IMU drift, which is if you've got something flying fairly consistently in a straight line, the IMU begins to drift and lose its accuracy. So ways that you can do it, or what you can see, is the drone may stop suddenly and then go backwards and forwards a few times. This just helps calibrate that IMU and get it back onto a more accurate and suitable pathway for what you need for LiDAR processing. So what we do is we make sure that our IMU is calibrated every 90 seconds. And a form of calibration is when it does its turns from its lines and does the sharp turns. So that helps calibrate it as well. But if the flight lines are quite long, it might automatically create a calibration line. And if we think it is extending too far where it doesn't calibrate, we can manually calibrate it ourselves in the flight. And it is recommended because the IMU is such a big part of making sure that you get good quality LiDAR data. being able to calibrate your IMU is very important in the flight. And the next essential component is the GNSS receiver. So what we need for our flights is an RTK GNSS receiver. And unlike photogrammetry, we don't need RTK to produce results, whereas with LiDAR, RTK is critical. So what we do is two options. We can use RTK via the CORS network. So that's a network RTK solution. Or what we can do is a base station. And either of the two we found give you similar results. So it's generally we would probably use a network RTK solution if we're in good phone reception areas, and we'll use a base station if we're in more remote areas where your phone reception signal may be a bit weak. So either of the two is important, but yeah, we do have those two options. We can do a base station or we can do network RTK. And one of the last but really important things that we do is we cross-brace our LiDAR data. So the term cross-brace essentially is, just say you've got a site and you're flying your flight lines for your LiDAR north-south in direction. Generally what we will do is a LiDAR flight. After this is done, we'll do a cross-brace LiDAR flight. So this may be 3 lines east-west, one at the top, one in the middle, one at the back, or doesn't necessarily have to be perpendicular to your LiDAR flight. You could fly on an angle, it can be a little bit more efficient, so it might be a V-shaped flight to cover up your area. And what this does is, in the processing stage, help reduce the point cloud or help increase the point cloud accuracy. There's another processing step that we use called strip align, which helps tie down any of the errors that are associated with each of these flight lines, and the slight decrease in accuracy with those angles, particularly towards the extremities of the swath angle, or the angle of the point cloud when it's the sensor sends out all the lasers when it's measuring. And of course, the last thing with the field processing or the field work is you cannot verify your data without ground control points and profile checks. So what we have, we'll often place ground control points or GCPs, similar to photogrammetry, all throughout our site. The targets themselves are a little bit different because when you look at your LiDAR data, you're looking at a point cloud. So it's a bit harder to actually see what you're looking at with a point cloud rather than photos. So what we do is we paint larger targets, and often this might be 2 big squares in one color and 2 other squares as another color. So it's basically one big square all up, which is quite easy to see with a point cloud, and you can, especially using different colors for these 2 different squares, you can really see it on the point cloud and when it's on your screen, and be able to manipulate or determine the accuracy of your data. And this is a really important step, particularly for surveyors, to understand how and verify the accuracy of your data. So what we will do is paint a number of ground control points all throughout our site, as well as profile checks throughout our site too. So the term profile checks is basically when we create a surface or a DTM model, we use these profile checks to measure the difference between what we actually measured on site and what the point cloud or the LiDAR unit determines as the ground. And if the ground or the LiDAR ground and the measured ground vary to a certain extent beyond what we're expecting, then obviously we need to do further refinement with the point cloud, or potentially use different surveying methods for the ground modeling. Which an example might be if you're on a site where maybe there's long grass exceeding the point where LiDAR cannot penetrate through the grass to the ground, then your accuracies will decrease, and it may decrease to the point where your results aren't acceptable for a DTM mesh. So in that case, what we will do is not use the LiDAR data for that DTM. So we'll then go and measure it in a different way, which may be total station, or it may be using our GNSS receivers, and then merge all of that data together to produce just a single DTM of the ground, which is within our accuracies that we need for the job. So now we're going to processing. This is very different to photogrammetry, and it actually is quite complicated. While LiDAR may seem to be fairly simple, it may be drag and drop your data, here's a result. What we like to do as surveyors is really refine and verify the accuracy of this data. So this is where a lot of problems can happen with LiDAR data and photogrammetry data, whereas you get a simple point cloud, or you do your field work, you dump it in a software, you get a result and then send it away. It has caused a lot of headaches and problems with sites because the accuracy of this data isn't verified, and there's no post-processing done. So there's no refinement of this DTM model, and it's not verified and it's not accurate. So what we like to do is make sure that we know and verify the accuracy of this data. So what we will do, some of our sensors have different processes with them, but if you've got a DJI sensor, what you have to do is your first step, post-processing through DJI Terra, because your data is with a DJI unit. The data in it is encrypted, so you have to bring it through DJI Terra to get your initial result. So we will do that. We will do our field work, dump it in DJI Terra and produce an output, and then from that we export all of this data into another software, and this software we use is called LP360, and basically this is a LiDAR processing software, so it's specifically good for LiDAR processing. What we found is it's actually amazing with LiDAR data, and a lot of data too. It can handle quite sizable jobs very well, whereas a lot of software, particularly with LiDAR, can have a high amount of data. We could be getting 100 gigabyte of data for one job. A lot of software really struggles with this amount of data, whereas LP360 is great, it handles it, and it's just fantastic with the processing speeds with this amount of data. So using LP360, what we will do is further refine and post-process this data. So one thing we do with this is shift and translate. So what we will do, there is slight differences with point cloud data being on a certain system. Often for us it is MGA 2020. There will be a slight shift from our measured point or our point cloud to MGA 2020. So what we will do is shift and translate the point cloud to be more accurate on MGA 2020. And the next step, what we will do then is scale it from grid to ground. So because it's GPS data, it's all on a grid system or grid MGA 2020. We want to scale this to ground coordinates to be what you would actually measure on the ground. So we scale our point cloud data, and after that, the next processing step we do is called strip align. So this strip align helps correct for the every line of data that you've got produces error, particularly towards the outer extents of the data. So what this system does, it uses that cross bracing that you've done in the field to help refine all of these little areas. So basically it tweaks up the point cloud to more accurately match in with each other, and where the data doesn't match is what we often refer to as cheese and bickies. So basically what we're doing is reducing the amount of cheese and bickies, or the error in this data. The next step with LP360 is smoothing. So what this does is basically when you use LiDAR, there's an element of noise, what we call, and that's the difference from the highest point to the lowest point of data. So particularly with cheaper sensors, LiDAR produces potentially 150 mil of noise, which is a variation of points within 150 mil of each other in a certain spot. What smoothing does is eliminate the extremities of this noise, and it basically thins it out to be a smoother point cloud. It doesn't do this with spots like vegetation or trees or anything, because there's that large difference. You might get the top of a tree and grass, so it doesn't do it there, which is good, but it's a really good algorithm to help reduce the amount of noise that's with your point cloud. And this really helps us with our DTM modeling further down the step of our processing. The last step we do with LP360 is reduce the amount of points we have, because this software handles a very large amount of data and others don't. What we do is thin out the point cloud. So rather than being 100 gigabyte in size, we can reduce this down to just so we want 100 mil spacing between points. It could make the point cloud size a tenth of the size. So it's a fantastic way for us to export this data and read it in other software, which is important for us for our DTM modeling. So we will get this large point cloud, reduce it, and then we can then export it to our next software. And the next software we use is Trimble Business Center. This has a fantastic point cloud classification tool, where basically what it does is reads your point cloud and it can classify each of these points into different, we'll call them groups. So one of these groups might be a ground group, and one of them might be a vegetation group and a building group. And what it will then do is classify or determine each of these points and put them in a group. And TBC, while it's not perfect, it's a really good tool at doing a big overview look of a site, a very large site, and classifying these points into groups. So then once we have our ground group, we do a little bit more refinement and excluding and including certain points out of groups and into groups, because it's not perfect. We'll refine a little bit, and then we'll have our ground group. And this group is important for us to produce that DTM or ground model. And from there, we will export this into another software. So as you can tell, for us, LiDAR processing involves a lot of different software, and here's another one that we use, which is called 3D Reshaper. And this one is a fantastic point cloud manipulation software. So from here, we'll have our ground group, and what this software does is help refine the point cloud even more so. So we will then start to exclude things like edges of buildings or things that the Trimble Business Center classification tool doesn't quite exclude very well. We'll do further refining. We'll try and eliminate grassy areas a bit better, get rid of the trees and vegetation or any features that we don't want part of the DTM. And then from there, we'll then do a DTM generation, which 3D Reshaper is fantastic for. It's got a great tool for creating DTM models, which is the DTM model which is commonly used is triangles or 3D faces. And what this software does is use the point cloud to create a DTM model. And from that, we have this large DTM model, which then is refined and reduced, because often this software can create a DTM model with millions of triangles in it. We can then reduce it to be a little bit more friendly for other software, which include something like your typical CAD package. So this software, again, can read quite a lot of data and reduce this data really well too. So that may be another step that we do, is reduce the size of this DTM model to something a lot more user-friendly And often you'll hear complaints about point cloud data and how, because of the size of the point cloud data, it's just not usable for people to use. So this software is fantastic for reducing these triangles and making it a lot more user-friendly. And the models that it creates from it are fantastic as well, so we can then export it into your CAD package. And it doesn't have to be that format, it could be other formats depending on the end user and the result that they need, but typically we will do a CAD package format, so we'll send these triangles to a CAD drawing, and what we'll do there is merge it with other survey data as well. So we might be doing something like a feature and level survey where we need to include a DTM model and other features picked up on site, and possibly maybe title boundaries. So we'll have all of this data merged into one big format, and then be ready to send to an engineer as an example. So yeah, the LiDAR data helps as part of this survey output to send through a DTM model. It may have power lines in there as well, which we can convert from point cloud data to polylines if that's required, or some kind of CAD ready output. And yeah, we can have this one big package that's simplified and a lot more easier to use, rather than just one big heavy point cloud, which is often very difficult for people to understand and use, particularly with the software that they have on their end. They may not even be able to read it. So yeah, the LiDAR data itself is fantastic, particularly if you have the software and knowledge to reduce it and make it a lot more user-friendly, and cater these outputs for the end user. So there you have it. LiDAR data is amazing, and the technology that particularly today is it can cover such large areas really quickly. It is a fantastic tool that we use all the time with our survey equipment. So if you have any questions about LiDAR data or any other questions about survey related topics, please reach out, send through a message. Otherwise, thanks for listening.